Yeah, so obviously over the last few weeks we've been talking about all sorts of things that our robot gets up to inside his little room, and all of the weird analogies we've come up with along the way, including fighting fantasy books, which is fab. But what I want to do now is show how it all fits together in context. I want to sort of do it by way of review and by sort of challenging you, Sean, as to how much you've remembered about what it is these conversations are. So,
crikey.
I know it's a bit of an ask, right? But we'll see how we go. What I really want to do is show how a super simple operating system could load up two programs, one of which will of course be the Fibonacci program, don't worry, we'll have that, and another program, and then have them running apparently at the same time, and how that might be built out of the components that we have assembled so far. You know, one of the things we know is that we only have one CPU in our sort of made up computer, and in most modern computers you have multiple CPUs, but like it wasn't that long ago you only had one CPU, but even then you'd be running Windows and you'd have multiple programs up and running, and it would appear like they're all running together in beautiful harmony. And so let's see how we can kind of build that out of what we've got. So I'm going to start by saying that each of our programs needs to have its own independent view of what memory looks like. Now, if you remember, there's a way that we can do this. So what would our operating system have to do in order to give a program its own view of what memory looks like?
Well, it's going to be remapping, or certainly presenting something to the program that the programmer's expecting, but maybe doing something different behind the scenes.
Exactly right. Yes. So what I've got here is my too terrible because I couldn't find any post-it notes in my entire house in the 10 minutes leading up to this. These are my two sort of slabs of memory that I'm going to use as sort of descriptions for both of the running programs. And this is going to keep track of what the operating system is going to have stored individually for each program that we're running. And we're not going to go into how the programs are loaded and all that kind of stuff, right? So, but or maybe we can at the end, but we'll see how we go. Let's start with this. So I'm going to say that somehow the operating system has 2 pages of memory to start with, and each page is going to just store information about each program. So this is going to be program... we're going to call this program 0. In fact, I'm going to call it, sorry, I'm going to start again, because that's a terrible name, because it is a program, but you can run multiple copies of the same program. And so really we need a better name than program. Otherwise it would imply there is, one program has one execution. And I'm going to call this a process. A process is going to be a running version of a program. So this is going to be process 0. And then we need to store some information about process 0. One of the things, the first thing we're going to put down is what is the map of the memory that this process is going to see. Exactly as you said, each process is going to need its own individual map. So there's going to be a set, and I'm going to simplify it because I haven't got enough bits of paper here. But really, as we discussed in a previous episode, we're going to have one pointer that points to the first page, which is the first page of our book that tells us, follow this set of directions to say how each memory location maps to this process's view of memory. And so I'm going to call that, we'll call it the page table pointer here. So we're going to have a page table. This would actually be a pointer to some more memory blocks that we'd have to have over here or whatever, but I'm just going to draw it in this page, or on this piece of paper at least. And so what we're going to say is somehow address 0 for this process maps to, I don't know, RAM cell 12, and address 1 to 13, and address 2 to 14, and this would be like 0, 0, 0, 1, 0, 0, 2, 0, 0 mapped to these 3 pages. I picked some numbers just to show that that's where this process is memory going to be. And what we'll do is we'll arrange for the process's program to be loaded into one of those. Let's say we're putting a address 0, which is usually a bad choice for programs because 0 is usually special, but for the sake of argument, we're going to load our program into physical memory cell 12. And then we'll start running it from address 0 once we've set up this page table, because now it looks like 0 maps to this particular physical page. So that's so far so good. All right. Now, for a single process, this is probably all we would need to do. Our operating system would set up this paging table, load in the information of the executable, the program, the actual bytes, the zeros and the ones that correspond to the program makeup itself into like address 12, block 12. Set the page table address to point at wherever this is in memory, and then it would just jump to address 0. And again, because we have been in the operating system, if you remember, the operating system has certain privileges. It can do things like monkey with the page table. And it doesn't want, I don't want my Fibonacci program, let's call this a Fibonacci program, to accidentally access things it shouldn't do, or, you know, change the page table. So do you remember there's a special privilege that the operating system has, and I use one name for it, if you can remember now. This is definitely challenging you, isn't it? I know, I'm sorry, it's mean.
How many videos back are we going here? Is this...
This is probably 3 or 4 ago.
No, it's gone. Go on. Give me a hint.
This is supervisor mode, or kernel mode, or in x86 ring 0, ring 3. Yeah, that's right. You remember some of these things. We went through all these, and there are some other things. But yeah, so the last thing that our operating system would do before it jumped to the beginning of our Fibonacci program would be to take away its own privileges and then jump to address 0. And then our Fibonacci program would start running. Off it would go, fantastic, and it would start writing to maybe address 100, and then that would be where the Fibonacci sequence would start and all that kind of stuff. And then, of course, it would actually run out after a few Fibonacci's because we've only given it this much memory, and then bad things would happen. We can actually talk about that at the end, but that's great so far. All right, but the thing is, we also want another program to run. So over here, we're going to have process 1, and in my terrible handwriting, which is Sean's Mandelbrot generator, which I'm assuming you've meticulously crafted in assembly code.
Very carefully. And
that will have its own page table, of course, over here. And its mapping of 0, 1, and 2. Again, they're only going to have 3 pages because I can't be bothered to write them all out. Let's say you have 20, 21, and 22. These physical slabs of memory have been allocated to your process. And that's great. So now we've got 2 processes, but only 1 CPU. Assuming this has already been set up somewhere, our Fibonacci program is running over here, and that's what it'll do until the heat death of the universe, right? There's no reason. Our Fibonacci program doesn't stop for anybody. I mean, he'll run out of memory first, and then it'll be a whole thing. But let's think about what we could do in order to sort of have both of these running at a time. So first of all, the first observation is humans are really, really slow compared to computers. I think we discussed this in one of the earlier episodes about how many orders of magnitude difference. So what we would like to do is do a bit of Fibonacci, and then go over to the Mandelbrot and do a little bit of Mandelbrot, and then come back to the Fibonacci, and then just go back and forward between them. And if I do that fast enough, you won't be able to tell that they're not running at the same time. Now, each of them will be a little bit slower, of course, half the speed. Now, one thing I could do is I could write my Fibonacci program so that at the end of every number it calculates, it calls the operating system and says, I'm finished for a bit, let someone else have a go. And similarly in your Mandelbrot program, you could say after each colour, each pixel you've plotted, you say, hey, now it's someone else's turn. And in fact, some of the earlier operating systems that I grew up on, so those Brits who have had an Archimedes or any of the Acorn machines, or in fact the very early Windows machines, so Windows 3, use something called cooperative multitasking, where each process actually cooperated with the operating system to say, I'm finished now, let someone else have a go. And that's very lovely. Unfortunately, though, all it takes is one programmer mistake to not give up, and then suddenly the computer becomes unresponsive. And obviously that's not a great feeling. We've all had an unresponsive program, but it's not very often that the mouse itself stops responding, or you can't just switch away to another program and then kill the first program. So that's not a good way forward. And, you know, it has its advantages. It's certainly simpler. But what we want to be able to do is force these 2 programs to cooperate with each other, or rather at least cooperate with the operating system and share time. So let me ask you, if you were sat and you were editing a video, and I know that you were like deep in the thought process. I'm sure it's incredibly absorbing activity to be thinking about how all the things are going to fit together or animating, but you knew you had something else to do as well. How would you deal with that? You know, let's say you just want to say, I'm going to do an hour of video editing and then I'm going to do something else. How might you personally?
The obvious answer here is you would stop doing one and go and do another and hope that everything is saved as you left it when you come back to it. I would probably use copious amounts of post-it notes and notes to try and remind myself where I was at.
Exactly, that's an important part. But how would you even know when it was time to go and switch to another task? What would you do?
Oh yeah, I'd set a timer probably.
You'd set a timer? Yeah, exactly. I would set a timer on my phone. Now, because we're in the 1980s, we don't have phones. But what we probably do have is a little kitchen timer. You know, the type with the mechanical kitchen timer. You turn the thing round to like 30, and then it would clockwork going down, and then it would ring. So we're going to give our CPU, or at least the computer the CPU is in, a special device that is essentially a glorified kitchen timer. And so the operating system will, before it starts a program, it will set a timer in this kitchen timer. It will count down once every cycle. So we'll put like a million, the number of million into the counter. When it gets to 0, the alarm will go off. Now, if no one looks at the alarm, no one will notice. So how can we make it so that nobody can ignore the alarm?
Well, does it involve the supervisor? Is this...
It does, but there's a way of us telling the CPU, the chip itself, hey, something interesting happened. You have to stop and do this.
Is this the interrupt?
Do you remember?
Interrupts.
This is the interrupt. Mm-hmm. So that's exactly what we're going to do. I don't know what I'm going to draw here, but you can imagine that there is a circuit outside of the CPU that counts down once it's been told, and when it gets to 0, its alarm going off is to set the IRQ pin, the interrupt request pin, on the outside of the CPU, causing it to stop exactly what it's doing and jump straight into the operating system and giving it back that supervisor ability. So what we'll say is after 100th of a second, our operating system will be returned to. So let's restate this. When we start our Fibonacci program, we're going to set up the memory this way. We're going to point the page table here. We're going to say, set a timer for 100th of a second, and then we're going to run the program. And so our Fibonacci program runs, thousands of CPU cycles happen, the timer goes off, the interrupt handler is called, and now we're suddenly back in the operating system. Now, when we discussed interrupts the first time around, we said that an interrupt was like a call that the program had run itself, in as much as it saves where it was before it jumps to the interrupt handler. So we know where it came from. So we know where in the program it was, because it could be anywhere. Our Fibonacci program has no idea that suddenly it's like had the gramophone needle yanked away from it. But we do remember where it was, to your post-it notes an analogy here. But we also know that the processor has various registers that we need to save. Now, last time, when we were talking about just a normal interrupt handler, what we would do is we'd save them to the stack, we would take care of our peripheral, because we were going to return back to the process that we interrupted. But here, what we want to do is return to a whole other process. So instead of putting it on the stack, what I'm going to do is here on my sort of process table that has the information about this particular process, is I'm going to remember the last state of the A register, the X register, the Y register, and the stack register for this particular process. And this is me pretending it's the sort of 6502-ish computer. So rather than push it to a stack, I'm going to store it in this process. So maybe A was 23, Y was 77, no, X was 7790, stack pointer was 1000, whatever. However it was set up, that is the entire state of that program, along with the memory that's in banks 12, 13, and 14, which we're going to leave the heck alone, right? Oh, well, we obviously need to know the program counter to go back to as well, which has already been stored on the stack, so we'll go and lift that off the stack and store it here. And then we're going to say, well, what other processes are there available on this system? What else could we be running right now? And we'll make a decision. Now, this is where operating systems get very sophisticated, because they can say which are higher priority processes, which things are accessing, which things have to deal with, streaming webcams versus, just running the background task in your computer, whatever. But in this instance, these two processes are equally valid. So we're just going to try the next process that's ready to go. And this one we'll assume has already been running, just for the purposes of this discussion. So we also know that over here, we have A, X, Y, S, and program counter that were whatever the values were when we last interrupted the Mandelbrot program. So I'm not going to write numbers for that. You can invent your own numbers for that. So then instead of us returning from our interrupt handler back to process 0, we're actually going to switch over here. We're going to change the page table to point now at process 1's page table, which means that suddenly the memory looks all different. Again, we're in supervisor mode, so we probably have some clever way of reading both the physical memory of the computer and also the mapped version of the computer. I'm going to gloss over that for this purposes of not getting too bogged down in the weeds. We're going to load the A, X, Y, S and program counter from process 1, and then we're going to return to it as if it was the one that was interrupted. And now suddenly we're back in the middle of the Mandelbrot routine doing whatever it was doing when it was last interrupted. And of course, oh yes, we'll reset that timer so we have another 100th of a second before we get interrupted again, and then the whole process will continue, and we'll ping pong backwards and forwards between these two processes. And as far as me and you are concerned, both of these programs are running at the same time. Hooray! They're not, but they certainly look like they are. So that is called context switching. I know that Computerphile has covered this before, but I wanted to get here because it kind of uses almost all of the pieces that we've got so far. We know about all the registers that are inside our computer. We know that the mapping lets us give different views at different times. We know what interrupts can do. And one of the things these interrupts can do is give us a timer to switch backwards and forwards between processes and give them an equal slice. This is not all that common, actually, that we have this. It's only when you're actually running CPU intensive programs, that is, programs that don't give up the CPU. Now, we talked about cooperative multitasking, but effectively, if you say, if you write a program that says, hey, operating system, what's the next key press, please? Well, there isn't a next key press until somebody presses a key, generates an interrupt, the operating system. So what the operating system will do in that instance is you will call a function which is like get me the next key press, goes into the operating system. The operating system will mark your process as you're waiting for something. There's no point coming back to you. You've got nothing to do. And so it will move you into like a different list of processes, and it'll say, well, when a keyboard interrupt comes in, I'll reevaluate that, and maybe I'll bring you back, and then I'll wake you back up again and say, hey, I'll switch back to you. But until then, the Mandelbrot program gets the entire CPU to itself. And to a first approximation, almost all programs are waiting for something slower than them all the time, unless you're doing like video rendering or 3D rendering, or you're playing a video game which is trying to go as fast as it is. Most processes are sat there. So if you bring up Windows whatever, the Windows Process Manager, or in Linux Top or Mac or whatever, you'll see there's pages and pages of processes in your computer, but most of them are doing nothing most of the time. And so it actually appears like we're sort of almost back to cooperative at that point in view, because every time you like read a file or wait for a key press or wait for anything, you are giving up voluntarily your slice of CPU time to someone more needy than you.
In this instance, would the CPU take 100th of a second to do what it needs to do as well? The OS.
Probably not. In this instance, we're talking. I mean, it's one of the things that makes an operating system feel snappy. It's one of the parts of the deep kernel of an operating system that is often very carefully optimized so that you don't spend time doing all this bookkeeping of which process should I run next and how long does it take to switch between them. It's not free, but in the scale of things, 100th of a second is a reasonable time slice. I think Windows used to use like a 30th of a second, if I'm remembering rightly, and I think it's now, I think, relatively adaptive on other operating systems, and they'll do clever things like if there's exactly one process that's able to run, they'll turn off the timer. It's like no one can interrupt me except like an actual interrupt, like a network card or a hard disk or something like that. And certainly in like the finance industry, that we play tricks to say, I don't want any interrupts actually. What I'm doing is more important than anything the operating system can do, so we'll turn off those kinds of things. But yeah, it's not very long to switch between processes. Again, with our little 6502 here, we have like 4 registers, which are all 8 bits, so it's not very big. With a modern x86 type CPU, you might have to save all of the floating point registers, all of the extended multimedia instructions, some of which are 1024 bits wide. So there are some tricks of the trade to make that a little bit more efficient, but it's still pretty quick to switch between tasks.
And one last thing, you mentioned, what if one of these processes is working? I know we've got a hypothetical CPU and everything here, but would it have kind of a looping 100th of a second, sort of check in every 100th of a second just to see if anything else is needed, or does it just?
Well, if we were to do this as a cooperative multitask, or just in general?
I was thinking, so your process is running, but then a user comes along and wants to do something as well. How does that interrupting happen?
Oh, yeah. So like, to put this into context of, say, like a Unix environment, we would actually have another process at least over here, which would be the shell. like the terminal that you're typing in with the pictures and everything, and it will be sat there saying, waiting, please tell me when the next interesting keyboard event happens. And it'll essentially be not in this picture, but as soon as someone types a key on the keyboard and an interrupt happens, the operating system goes, wait a second, someone was waiting for a keyboard. Oh, now process 2, the shell, is ready to run and is put up in this list. And then when the next 100th of a second comes around, or immediately, and, the operating system might choose to just go like, well, why don't we've already been stopped, we might as well just go straight to the guy that needs it right now. And then that shell, for example, can handle things like, hey, you hit Control C, that's kill process. And it can say, well, kill process 0, do an operating system call that says, I need to stop process 0, and process 0 will be terminated in some way, and this will be thrown away and the memory reclaimed, and then we'll never go back to it again, and that kind of feel. So yeah, there's always something interesting, something listening to things like keyboard events that lets you handle stuff exactly like that. Yeah, and again, like one of the things you'll be doing is when you hit enter, having run a new program in that shell, it will call an operating system routine, which will allocate a new one of these processes and make a new program come over here. And now we've got 3 to run between, or 4 including the shell.
So imagining one of these processes, or multiple are running, but one of the processes and it's about to get interrupted, will it happen at the end of a set of code, or what happens if it's literally halfway through?
So that's a really good question. It literally happens at the end of the next instruction. So if there's an instruction that's running, and it gets complicated with the out of order stuff that we've talked about before, but essentially when we get to retirement, which is to say we definitely know the branch prediction has all been done correctly or whatever, each instruction that's running, we'll see whether or not that instruction had either been the cause of, because you can do software interrupts, and you can also read memory that is like bad, and that's considered sort of an interrupt, or there was an interrupt that came from the outside world, and this is the point where we need to stop. And it's literally in the middle of the code. There is nothing you could know about as the person writing the Fibonacci code that would say you could make any guarantees about where the operating system can say, you're done now, it's someone else's go. But the operating system should make that invisible to you, because it will replace everything back exactly the way that you left it, even though you just loaded the value 10 into the A register and you're about to store it somewhere. The only thing that makes that different is that when you've got multiple processes that are collaborating with each other, then potentially where you're interrupted might cause you to have only done half of some operation that some other process was expecting you to have completed. Now, that's a bug, and there are ways around that using locks and mutexes and clever things like that, but it becomes exposed when suddenly you're like halfway through something which from the outside world you wanted to appear atomic, like, hey, this either has to have happened or not half of it. But that's a whole other topic, in fact. And we probably don't have time to start that one right now. And it's going to be lots of clever instructions that I don't know how to write off the top of my head that actually calculate the square root of whatever is in T2 as it happens. And we'll come back to that in a sec. And so this instruction at line 1003 wouldn't be a square root.